So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be going over how you can use class activation maps in order to figure out where your convolutional neural networks are looking in Keras. Let's go ahead and take a look at how this works. Now, I'm sure you're aware of the attention mechanism. Using the attention mechanism, you can find out where it is that your neural network is focusing its, attention. Now, this works great for recurrent neural networks and multi-layer perceptrons, or also called dense neural networks in Keras terms. However, they don't work very well for convolutional networks. Now, what am I talking about? Let's go ahead and take a look at an example of attention for a dense network. Now, with a dense network, you are essentially trying to take a feature vector and you're trying to classify those features into a few different categories or maybe do regression. But let's just take a look at the example of classification for now. Let's just say that we've got a neural network where you've got the features, all right? So you have features, all right? And these features need to be fed into your dense layer. Now, on the way to the dense layer, you can go ahead and do some really interesting stuff. Like, for example, instead of sending this to another dense, right? Instead of sending that to, say, a softmax for classification, instead what you do is you do a little bit of a skip here. You erase these two layers for now, but we'll get back to them in just a moment. Then you go ahead and right after this dense layer, you add a softmax, okay? Now, what you do is you keep this dense layer the same number of units as there are features that you're feeding in. So, for example, if you're working with the iris data set and you've got, a 3-length feature vector coming in, and let's just say you want to reduce that, or you want to go and put attention, then you don't reduce, all right? In that case, you create dense that has an output shape of 3 as well. So you're not reducing, all right? You're just going from 3 features to 3 features again in dense. Now you're going to go ahead and put in a softmax, but you're probably thinking, well, how would I train this neural network? What kind of output are we going to expect here? Well, this isn't where your neural network ends, even though there's a softmax layer. Now, what's the output going to be with a softmax? Think about that. Let's just say we've got 3 values. This is not necessarily what you feed into a neural network. I'm just thinking of random numbers. Say 3, 6, and 1. Okay? These are 3 different numbers, right? We can put commas between them. Now, these 3 different numbers, let's just say we ran these through, through this dense and through this softmax. What would the end result be? Well, it would be a bunch of numbers from 0 to 1, the sum of which would be a 1. So it's a probability matrix. Now, let's go ahead and take a look at what those values might be. Maybe it's 0.15, 0.25, and 0.4, or 0.6 actually. And that would add up to 1. Now, what's so interesting about the attention technique is you can go ahead and take these softmax values and multiply them by the actual values themselves. And once you do that, you've got weighted features that you can go ahead and feed into another few dense layers. So basically what you're going to do now is you're going to have a multiplication layer, okay? So let's just say we branch out here and we have a multiply layer, all right? You're going to multiply the output of that softmax activation by the features that you originally fed it in. Then you're going to have weighted features that you can go ahead and feed right back into another dense network, all right? And then you can go ahead and do your final classification. So for example, if you wanted to have another softmax layer, right? You want to have another softmax layer, and this softmax layer is going to do the final classification. So you're going to have, one of say 2 classes here. Let's not take a look at the iris data set. Let's just say we're classifying into 2 classes instead of 3. Then you're going to have your final classification down here after your softmax activation. Now this is well and good for dense neural networks, and there's a similar technique for recurrent neural networks as well. However, convolutional neural networks, well, they don't play very well with this technique. In my experience, whenever you would try this kind of technique, it simply wasn't scalable enough or it wouldn't work well enough to be worth the extra effort. However, there is still a way that you can visualize where your neural network is paying attention without forcing it to pay attention. Like, for example, over here what you would do is you would force the neural network to pay attention in order to train the attention layers here and here. However, what happens this time with the convolutional neural networks and class activation mapping is you're not forcing the neural network to pay attention, you're just figuring out where it is that the neural network paid attention. So now how does this work? Let's take a look. Now, first of all, we've got to understand, how do convolutional neural networks work in the first place? Now, convolutional neural networks are interesting. The reason I say that is, let's just say we feed in one image. Now, this image could be, say, 224 by 224 in size. That's a pretty standard size for a neural network. Now, the problem with this neural network, not necessarily the problem, but an interesting thing is that you're not just going to be feeding in this one image into the neural network. That's not how it works. What you're going to be doing is you're going to be feeding 3 images into the neural network. 3 images that represent this one image. So, for example, let's just say that you've got, regular image. It's an RGB image, right? It's a red, green, and blue image. You've got 3 different channels there. So you're actually going to be taking 3 different images, right? Your red, your green, your blue, and you're going to be feeding those as channels into your convolutional layer. Let's just say, in Keras, that would be a conv 2D layer. And that's what you're going to be doing, and then you're going to go on and on and on in your neural network. Now, let's just ignore this input part for now. Let's get back to the convolutional neural network. This time, we're not going to be taking a look at the beginning of the neural network. We're going to be taking a look at the very end of the neural network. So, now towards the end, of course, let's just say we draw a whole neural network, right? You've got convolutional layers. You go down and you have more convolutional layers. Okay, so you have more and more and more. And usually your filters will get more and more over time. The number of channels will increase, right? This is not what an actual neural network architecture would look like. This probably wouldn't be very well optimized. But let's just say that you've got two layers with 32 filters, then one with 64, and then one with 128 filters. Now that means there are 128 channels in the final convolutional network. You've got 128 images that your neural network is working with. I say images in a loose sense because it's actually just 128 different channels that your neural network is working with. You could, of course, reduce or increase that based off of your neural network, but that's not a problem for now. Now, over time, unless you're doing things like zero padding, your neural network will reduce the dimensions of the image. That's just how these convolutional networks work. Of course, you could put zeros on the outside of the image, and that's how you would usually keep the image size the same. For example, in ResNet for skip connections, you kind of need to do that. However, for this, let's just assume that the size is going down over time. So if we start off with, say, a 224 by 224 here, this is going to go down to 222 by 222, then it's going to go down to 220 by 220, and then it's going to go down to 218 by 218, assuming that it is a 3 by 3 filter size all the way down. Now, the interesting part here, again, is that towards the end, let's just say, for the sake of simplicity for now, that we're working with a smaller set of images. Let's say we're working with 28 by 28. All right, and the 28 by 28 becomes 26 by 26, which becomes 24 by 24, which becomes 22 by 22. All right, now what happens at the end is we've got 22 by 22 by 128 set of data. All right, this is basically a NumPy array with this shape, okay? Now, what if there were a way to visualize the weights that the neural network gives for each of these individual filters at the end, okay, towards the final classification? Okay, that's what we're doing here with class activation mapping. There's a special kind of pooling. You've probably heard of maximum pooling, right? How you actually take, say, let's just say you've got a 6 by 6 set of data, right? So you have 6 different, or 1, 2, 3, 4. Let's just say you've got a 4 by 4 grid, all right? Now, let's just say that this 4 by 4 grid, or this 4 by 3 grid here, there. So now we've got a 4 by 4 grid. Let's just say that you want a max pool with a window size of 2 by 2. So what you're doing is you're taking the values from this window, you're taking the values from this window, you're taking the values from this window, and you're taking the values from this window, all right? And you're getting the average of those groups, and then you're putting them into a new image. This new image is simply, say, let's see here, 2 by 2 in size, and this is the result. All right, you know how to do this. This is simple convolutional neural network stuff, and it's stuff that you've been doing for a long time if you work with convolutional neural networks. But global average pooling is another really interesting kind of pooling. And what it lets you do is take this whole 4 by 4 grid, all right, and bring that down to not 4 different data points, but instead just one individual data point. So what you're going to be doing is not getting the maximum value from any individual group. You're going to be getting the whole average value of this whole filter, and you're going to be getting that down into one individual value. That consists of the average of all the values that you just collected. Now, what you can do with the possibilities that this opens up is that, well, let's just say at the end here, right? We've got 22 by 22 by 128 image. With global average pooling, using no weights, just this like averaging method for each of those 128 channels, you get down to a 1 by 1 by 128 set of data. Now with this 1 by 1 by 128 set of data, you can go ahead and assume that, of course, each individual data point, right? Let's just say there are 128. There are 3 here, so let's just say there are 125 of these, data points going forward. And let's just say you have 2 classifications, right? There are 2 classes that you're trying to classify into, over here and over here. These are your dense units. You can connect directly from this global average pooling and flatten layer to those units. Now, I'm sure you're starting to see where I'm pointing towards. If the final activation here is softmax or really anything else, what you've just done is you have provided a weight, okay? You've provided a weight value for each individual filter. Because remember, each of these individual data points came from one bigger filter in the actual convolutional neural network. So all of these came from different filters that found different shapes or edges in the image, and these represent those filters. So if you could somehow exploit the way that you're actually capturing those weights from individual filters to the actual units that have different meanings to you or your classification, you can go ahead and assume that the filters these represent contain meaningful information as to the relationship between a certain class. So, basically what I'm trying to say is that if you were to say, all right, this is a dog unit and this is a cat unit in terms of dog versus cat classification, if you go ahead and take a look at the weights from the dog unit to all of the different filters that you fed into that one individual unit, whichever ones are higher have a good representation of where the dog is in the image or what the dog looks like. The ones that are lower are capturing information that is related to anything but the dog. And that is what I'm going to be showing you how to use in Keras. I know it sounds really complex, but it's not nearly as complex as you may imagine. Now, what I'm going to be doing is showing you how exactly you can get a good class activation mapping, designing neural network architectures that are specifically built to work great with class activation mapping so you can do object detection directly within your object recognition or object classification workflows. This could be expanded to a lot of other places as well, but we're going to be covering convolutional neural networks for image classification in specific today. Alright, so now, without any further ado, let's go ahead and get into the code part where I'm going to show you how you can implement this system and take a look at where your neural network is actually looking. Alright, so welcome back, and now let's take a look at the actual code that goes behind this. Now first of all, let's take a look at the neural network architecture. So let's go ahead and open up, first of all, before we get even into the neural network architecture, the data loading script. Now, of course, in order to do this cat-dog classification, we're going to need data. This data has been downloaded from Kaggle, and you can do so as well. Now, this is a bunch of really simple code that I've put together that essentially uses multiprocessing as well as NumPy, glob, and pillow in order to load a bunch of images and then save them to the disk as dogs.npy and cats.npy. It loads them in at 224 by 224 resolution, and it does the necessary pre-processing, like for example dividing the RGB values by 255 to make sure they're good ranges for the neural networks to capture. Now, if I were to go ahead from here, as you can see, basically it's just using a multiprocessing pool in order to import images very, very quickly. Of course, multiprocessing, multi-threading, these kinds of things in Python don't usually work very well together, but in this case, it gave enough of a performance improvement to be worth the extra hassle. Now, if I go ahead and exit out of this here, we can get to the real main part, which is the actual neural network training that I do. Now, the neural network training, since I have 8 different GPUs on the DGX-1, I can actually go ahead and build the model on my CPU, and then go ahead and train it on the GPU, or specifically 8 GPUs. And because of that, I take my batch size, which is 64, multiply it by 8, so that, of course, I mean, that's 64 times 8, that's 512 being done in a single batch. Of course, 512 divided by 8 is still 64, so 64 images being done per batch per GPU, basically. Now, I'm doing 150 epochs, but I won't necessarily wait for 150 of them to be done. I actually have this callback that'll actually force the model to save at every single epoch, and also log down what epoch it was and the validation accuracy. And so basically I can go ahead and take whichever epoch had the highest validation accuracy into my experiment. Now, of course, in terms of test size, I'm keeping 20% of the data for testing and only 80% of the data for training, and I'm glad to say that I was able to get to around 91% accuracy using this neural network that is barely optimized for this kind of classification. Of course, I could get much higher if I did something like transfer learning or using larger data sets. However, for now, I'm using just a plain old new neural network using this global average pooling 2D layer at the end, and then directly a dense connection. Now, though, let's go ahead and get into how we can actually use this with CAM. Now, the beauty of this technique lies in its simplicity. So if I were to go ahead and quit out of this, I go ahead and take the trained model, save it to my disk, and this is where it's located, in the CAM folder, or class activation log. So we've got a few main files here. We've got the CAM file. Of course, we've got a cat picture, and we've got a dog picture over here. Now we've also got this model. This is actually what I downloaded from my Nimbic server. But there's just one little problem with these models. Let me show you. TensorFlow, Keras, models, import, load model. So I'm going to go ahead and load the model that I actually downloaded from my Nimbic server here.
Now, what you'll notice is that when I go ahead and load the model, and also just one more thing you should notice though, is that this model checkpoint, which is what I downloaded from, I told it to not just save the weights, but also to save the neural network architecture in the same file. So that's why I can just do load model without defining the model and then loading the weights. Now, if I were to print out a summary, you see it's not saved in the same format that I wanted it in, right? So we've got all these input layers, these lambda layers, we've got the sequential, and we've got this weird concatenate stuff. However, if you take a look at the layers, right, in the model, you take a look at this array, the second last is this sequential layer, which is actually technically a model. Now, if I were to take a look at that, that is indeed sequential. And because that model is a layer, I can go ahead and treat that as an individual model, which gives me this whole, this real sort of model, which is what I wanted. And so if I were to go ahead and actually save this as a model, it would go ahead and work because this is what I'm truly after, not this weird format of a neural network, because this has my global average pooling and my convolution layers. So I'm going to go ahead and exit out of this, and let's go ahead and take a look at the actual code. Now, the class activation map code, as I mentioned, is very simple. It's taking the actual weights from the final node that made the highest prediction or the highest confidence value, and it's trying to figure out which filters had the highest weights. Whichever ones had the highest will have more of their map added to the final class activation map. Whichever ones had less weights or less important weight will actually reduce their pixels or their pixels importance from the final class activation. There will be a link to where you can download this library or this function in the description below as well. I'm going to go ahead and quit out of this, but the really interesting part is inside of the make prediction file, because in the make prediction file I go ahead and actually use that class activation code. Now, in order to create a class activation map, essentially what I do is I run a prediction through the model, all right, and then from there I create a new total class activation map. I add all the pixels that are supporting that evidence for the main prediction that the neural network made, and then I remove the pixels that are supporting the evidence for the lower prediction. So, for example, if you were to put in a dog and the neural network predicted that this is a dog, it will go ahead and add the dog heat map pixels, and then minus the cat heat map pixels from that final class activation map. And then from there, it's going to go ahead and divide it by the maximum of the absolute valued total class activation map. It'll clip the values at 0 to 1, multiply them by 255, convert them to a uint, convert them to a real image, and then save it at a certain location, and of course return it as well. Now over here, I've just got some simple code to actually go ahead and load my image, put it into a NumPy array, and then over here I call that function with the image and the original one as well. So if I were to go ahead and exit outside of this file and run python make pred, I can go ahead and feed it a model, like for example the catdog.h5 model. Let's go ahead and feed it, a cat, let's say, cat.jpg. All right. Now over here, it's going to go ahead and run it through the model, and as you can see, with 99% confidence, in fact over 99%, it predicts that this is a cat, because the first class is indeed a cat. Now, what you can do is open this directory in Finder, and let's take a look at the cat and the cat's heat map. Now this is really interesting. Take a look at those white spots in the image and take a look at the cat. Now, what's happening is wherever the white spots are located, that's where the convolutional neural network was like, yes, this is part of a cat. And where the black spots are either A, not cat activations, or B, wherever there was a dog activation. So this is what the neural network is seeing when it sees a cat. Of course, there's a lot of room for improvement. We could have a more high-resolution class activation map. We could have a more accurate neural network. We could do transfer learning from something like from the visual geometry group, like VGGNet. We could do all these little, sets of fine-tuning in order to get a better class activation map and a better neural network overall. But let's go ahead and take a look at the dog now. So if I were to feed in dog.jpg, as you can see, it runs it through the model, and it lets me know that with 77% confidence, this is indeed a dog. I go ahead and open up both those images, show them side by side, and as you can see, well, I'm going to go ahead and split these up into two different windows over here so that you can take a look at them and switch them over so we're consistent. Now, this part of the image over here, which is of course near the dog's head and ears, is what really activated the neural network to say, yes, this is a dog. And so did this lower part over here towards the bottom, and so did the dog's tail. So as you can see, the neural network is definitely basing a lot of its predictions off of the animal's tail. You saw with the cat, you see with the dog, it's trying to find some sort of patterns in the tail that say, yeah, this is a dog tail, or yeah, this is a cat tail. And it's also taking a look at those feet, for example, it's taking a look at those arms, it's taking a look at all these different things in order to make its final prediction. Of course, this can be used for debugging your neural networks. This can be used to figure out whether or not you're finding the right features within your neural networks as well. And that was a quick demo of class activation maps through Python and Keras. There's much more to come when it comes to class activation maps and object localization using neural networks only trained for object recognition. But that was a quick tutorial on how you can use class activation maps. I do hope you enjoyed. Thank you very much everyone for joining in today. If you did like this tutorial, make sure to leave a like down below and share it with your family and friends if you think they could benefit from it as well. Apart from that, if you do have any questions, suggestions, or feedback, feel free to leave that down in the comments section below. Or if you do really like my content and you want to see more of it, feel free to subscribe to my channel, as it really does help out a lot, and turn on notifications if you'd like to be notified whenever I release new content. So again, thank you for joining in today. That's what I had for this tutorial. Goodbye.